I love applause at the beginning. So I'm Matt Turk. I'm from University of Illinois, and Kester Tong from Google is going to be giving the second half of this talk. My half is going to be sort of the technical side of things, and then Kester is going to move on to, I'm sorry, the lower level systems stuff, and then Kester is going to talk about some of the higher level technical aspects. I also wanted to mention some of the stuff I talk about in here was done in collaboration with Sam Skillman and Mike Warren, who are in the back of the room, and I think between them they have something like 8 terabytes of data on their hands if you want to sprint on data stuff later on. I wanted to also really quickly thank the Google team that has been working on this. Many of them were here earlier on in the week and even still, but Sam Clegg, Molly McKinley, and Ben Smith from Google, from the native client Chromium teams, have been just amazing resources throughout all of this. But also the native client team, the Chromium team, and of course the IPython team. I wanted to start out real quick just by one of the things that I took away from this, which was super fun. This is my OLO graph. And then you'll note that, I was proud of it before, but in the last 6 months, I've actually had 5 commits into Chromium. And so this is, like a badge of honor. I don't know where that goes on my CV, probably under synergistic activities, but 5 commits to Chrome. I was super happy about that. So the quote that sort of drove all of this is from a computational scientist named Bronson Messer. I heard him say once at a conference where he said that there was a particular moment when he was working with a student, and it was that moment when they realized that they can bend their computer to their will. It's this empowering moment where you realize that you can do something. And in the last year or so, I've realized that what I want to work on the most is actually that moment when people realize they can bend the data to their will, when they realize that they can ask questions of their data. This is a picture from a workshop that I worked at about 1.5 years ago, and someone stood up and she said, after this week, for the first time, instead of using someone else's Fortran code that I had no idea what it did and just produced a series of numbers, I've actually been able to look at the data that I was using. And this was super cool. Anyway, what drove me to this project was something called the dark sky simulations. And this is a trillion particle simulation that was run on something like 5 digits of cores at Oak Ridge, 6 digits of cores at Oak Ridge over the last 6 months or so. And the thing about these simulations, and you can actually read our paper and all this stuff, it just came out today. You can go to darkSkySimulations.info and find a 32 terabyte file to play with, is that for the most part, simulations like this don't get a lot of citations. They don't produce a lot of scientific inquiry, right? If you look at the graph of particle number versus the year, you can see that the particle number goes up like you wouldn't believe. And we've circled the we've indicated the Gordon Bell prizes here. And you can see, and it was said the other day that Python people don't win Gordon Bell prizes. And I don't actually know how true that is, but you can see that no matter how big something is, that doesn't correlate with how useful it is to the community. And part of this is because it's hard to get at the data. And there are a couple different ways that you can do this. Like for ours, we had several different options. We could tell people, well, just get an allocation at Oak Ridge. Then you can do whatever you want with our data. Or we could say, mail us 3 dozen hard drives. But nobody wants to do that. And then the final one was actually, this has been the most successful one, is go ahead and type your SQL query into this form. We're going to rate limit you at 50,000 results. And this, to me, is akin to handing someone a pair of boxing gloves and saying, I'm going to send you an email every single week, which you need to respond to. And the thing is, you can't do that forever, right? You can't type with boxing gloves on. And so we asked ourselves, how can we make this data available without compromising the ability of individuals to self-direct their inquiry? So, you've got a person, and they've got their data. And then what we would always do is we would use a Python package called YT to access that data. And now as the data gets bigger and bigger, it becomes much harder to ship that data around. And really, YT is not the real point here. The point here is that people like to use code to access data. And YT is really at the bottom of this, or well, top, but I guess I drew it at the bottom here, of a stack of different community-based codes. Python, NumPy, H5Py, Cython, Matplotlib, IPython. And that's the way that it is for many people in the community as they're developing an ecosystem of analysis. But getting these things to people can be extremely difficult. And this compromises their ability to ask questions of their data. So Python mediates this, and it mediates it through a couple different ways, right? Python can be mediated, can be communicated with through input-output. So for instance, things that are on disk. It can be mediated through standard in, standard out. As you're typing something, it talks to the Python kernel, it talks to these different things. And it can be mediated by a GUI. So for instance, you might have a GUI layer on top of a Python analysis package or something like that. And the way that Python talks to the data is the other half of this equation. Now typically it talks through some form of POSIX, because while I've heard that people use Windows for this, I haven't seen it in action. And that thing about POSIX is that's so beautiful is that everyone knows it. It might not be great, it has a lot of shortcomings, but everybody implements it. And so what we wanted to do is we wanted to identify how can we make it really easy for people to get at their data using these interfaces they're already accustomed to. But what we didn't want to do is we didn't want to enable just crazy times, right? If you say, go ahead and send me a Python script, I will run your Python script on my, I will use my one-time pass to log into the supercomputer and run whatever Python script you send me. They can do crazy things. They might remove things, or they might allocate a trillion particle long array, or they might send a flagrant error. I thought that was going to go over better than it did. So what we wanted is we wanted a way to sandbox it. And it turns out that there is a way to sandbox process execution. Now, of course, we're all familiar with virtualization, and virtualization is in fact a security mechanism. Docker famously is not a security mechanism. And what we want, but there's another one out there. And this one was called Native Client. So Native Client is a component of the Chromium project. And what it is it provides a sandbox for executing processes. And these processes have clearly defined input-output mechanisms. So for instance, these processes can communicate using what's called a Pepper API. The Pepper API defines a set of things that can be passed in and passed out from one of these running sandboxes. And these things can include stuff like strings, arrays, numbers, images, OpenGL context, sockets, gamepads, I think Oculus. And what we did was we wrote a wrapper for some of this. And this wrapper was called PPAPI, because PPAPI is the namespace that all these things exist in. And we provided a mechanism for serializing without conversion to JSON using the WebSockets that Native Client uses internally. Things like strings, NumPy arrays, and even file systems, which I'm actually not going to demo today, but given the right permissions in a packaged app, you can open a file system and expose it to a running process inside Native Client. And the other way that Native Client provides for communication mechanisms is through a POSIX-like wrapper level called Knakal IO. And Knakal IO provides the ability to mount file systems, sort of false file systems, but also kind of real file systems, because really what is a file system besides something that implements the POSIX file system standard? Such as HTTP file systems. So if your web server sets up the CORS headers correctly, you can mount it as a file system. So for instance, we're not going to show this, but we set our paste bin to export CORS, and so you can mount the paste bin and just run any script in the paste bin. It can do HTML5 file systems, which can be persistent, temporary, or even locally found file systems in HTML. So that would mean that I can choose a folder on my hard drive that I want to open up and expose to this running process. And then things like memfs and Fuse and PyPPAPI is just about ready to implement Fuse file systems. And you can do sockets as well with the right permissions. So the process goes something like this. You write an application. So here is the Zen of applications, and that gets compiled to a.out, right? That's what we're all used to when we run GCC or whatever on our local machines. Then a.out is executable if it's it's in the ELF format. So with Native Client, there's actually an additional step, or there's something of an additional step. What happens is using the LLVM toolchain, Native Client will compile down to an intermediate representation. And that intermediate representation provides sanitization for any number of functions that aren't safe. It provides the sandboxing mechanisms that are necessary, and then that intermediate representation can be translated to ARM, x86, i386, on and on and on and on. And it's something like 90% of machine code efficiency. This then gets translated into a NEXE file. This NEXE, or native executable, is then machine specific. So it still needs to be loaded inside a secure ELF loader, but it's raw machine code. So this executable has two different modes. We can construct what's called an unpackaged app. This can live anywhere on the web. So that would be creating a PEXE file. You go visit a website, and that PEXE file can be Vim, it can be Toybox, it can be BusyBox, it can be Python. There are PEXEs for Quake. There are all these different things inside the Knakal ports library. And if you're visiting that in Chrome, it will run at nearly native speed. The thing about unpackaged apps is that they also require an additional sanitization step. Because they're running anywhere, they can't have sockets, they can't have access to your local file system, but they can live anywhere. The alternate is the packaged app, and you'll see that I've cleverly made the arrow slightly bigger because it can do more. They can have sockets, they can access local files, and they need to be distributed through the Chrome store or live on your local machine. So this is great, right? If it's a pure Python system that you're trying to port. But if it has C modules, this has substantial caveats. So the caveats are you need to sanitize your function calls manually, and we've done this for a bunch of these Knakal ports. You need to disambiguate symbols. So for instance, in pandas, they override things like is leap year, and so we've created prefixes for those, such as pandas is leap year. And you need to add to the build, and this is actually the trickiest part. It takes about 26 minutes to compile and link an entire PEXE, because what it has to do is it has to compile everything into a single static intermediate representation. So you get two different things. You get a python.pexe, or a kernel.pexe, which can be executed from Chrome, which Kester is going to show as soon as I quiet down up here. And then there's the alternate, which is a python.pexe, which you can execute from a secure loading environment, cell LDR. So what that means is that you can translate it to a native executable that runs on any machine. Android was just added. And the question becomes, does this solve the build problem? And the answer is sort of. We can run these inside supercomputers now. So we've run some of these on Titan at Oak Ridge, but the thing is that they're still limited to 32-bit pointers. They can have 64-bit offsets, but 32-bit pointers. Does it solve the import problem? And kind of. If you use all the Pepper APIs, importing is ridiculously fast. But that needs to be added inside an additional loading step. And the final question, which I will then leave to Kester for the demo, is does it have to look like Python? Do you need to type in and say import this, blah, blah, blah? And the answer is absolutely not. So what this opens up is it opens up the ability for websites out there to have a clear mode of communication with a running Python kernel that don't expose any Python console. So if you have a way to generate map tiles, that can be run inside Leaflet now, dynamically, completely client-side. So all the code is available. Everything that I've talked about is and has been open source for some time. You can go to gonakal.com to find out some stuff. And then all the Knakal ports, which include all the Python modules, are in the Knakal ports repository on Google Code. And again, thanks to all these people, and I will turn it over to Kester.
Okay, so let's use your machine actually, because we're importing widely on this.
Oh yeah, and of course the whole point here is that we released all this data and we're putting notebooks out there that can use it. So there's going to be debug output in this.
Can you also go to my presentation first?
Oh yeah, of course.
Cool.
There you go.
All right, so I'm going to be talking about the Colaboratory project. And the starting point of the Colaboratory project is the IPython notebook, which I'm sure you're all at least vaguely familiar with. We wanted to do two things with the IPython notebook. We wanted to do this by bringing web technologies to the IPython notebook. So firstly, we wanted to use a portable native client to make it easier to install, and we also wanted to use Google Drive to make it more collaborative. And in order to cover all the possible use cases, we actually ended up producing two products. So the first one is what we call the classic Jupyter web app. And what that is it's exactly the same kind of user experience as Jupyter or IPython Notebook. So you go to you produce run a server on your own computer which produces a web browser, and inside that web browser in IPython Notebook that would talk to your local file system to get these notebook files, but in Collaboratory it talks to Google Drive, and then it uses a real-time API so that you can not only load and save files from Google Drive, but you can do it collaboratively in real time with other people, so they can make edits. You'll see those edits immediately, just like with Google Docs. And the other thing we wanted to do was give a seamless one-click install experience to users for people who didn't want to have to bother with installing IPython. So some people really need to have the installation on their local machine because they want it customized. Other people just want a single app that you can download with a single click and it's going to just work. So in order to do that, we needed the Pinnacle kernel because we wanted to do everything in a single Chrome packaged app that you can download from the Chrome Web Store. The participants in this project are Matthew Turk, myself, also at Google we have Kaya Patel and Mark Sandler, and then we're now working with the Jupyter development team. So the reason we wanted to do Google Drive integration was to make collaboration easier. So I'm sure you've all experienced the hassle of emailing files backwards and forwards, and even GitHub isn't always that easy to use. We wanted something where it's just as easy as Google Docs to collaborate with other people. So as you can see here, in the Collaborative Notebook, you can see who's in the notebook, you can see where they're editing the notebook or what they're looking at, and then you can see their edits come up in real time. The Chrome packaged app, what this is basically a web page in a window. So a web page dressed up like a desktop app. And it comprises both the JavaScript web style front end along with the Pinnacle kernel running in the background. And all of these things get packaged together and uploaded to the web store. So when the user downloads the app, they get all of those things. And it's a front end which written in JavaScript which talks to the Google API servers. And that's how we implement the real-time collaboration. So when you put these things together, you get the Collaboratory Chrome app. And it's easy to install, it's cross-platform, it'll run on any platform. It's also more secure because it's not running with your own permissions. It's running in the Pinnacle sandbox, which is completely isolated from your system. And this is great for things like education, because a person doesn't have to know about what's safe to run on their machine and what isn't. They can just run whatever the code they like, and it's going to be completely isolated from their system. Although you can actually choose to give it some permissions, like permissions to access Google Drive, if you want your code to be able to do that. By default, it has no permissions. And it currently has NumPy, Pandas, and Matplotlib. We're doing a sprint for SciPy, so please look that up if you're interested. SciPy is more interesting because it's written in Fortran, and we don't yet know how to port Fortran to Pinnacle, but it's going to be interesting to try. So I'm going to now switch to the app. So this is the Chrome app. I'm going to create to make a new document. So it says Pinnacle initializing, which is great. That means it's got that far. Okay, so import YT. Wow, that worked. Great. So let's open up the. It didn't work on my machine.
Oh yeah, no, that's good enough.
Wait, I'm just going to open up the. Oh, that's no good. Could you get to Google Drive so I can open up the actual document, that demo document?
Just show some of my stuff.
Okay. So,
because that was too much of a success.
Okay. So I'm going to show the my PhD is actually in economics. So I'm going to do something I'm uniquely qualified for, which is to simulate the stock market. So I'm going to import. I'm going to use PyLab, which is basically a matplot. It's a MATLAB style plotting in IPython. And now I'm going to use NumPy to generate some random numbers. So x equals NumPy dot random. Just ignore these outputs here. Dot normal, because stock price.
Those are all my fault, by the way.
So you can see what I'm using autocomplete here. So this is another great feature of Python, which is also part of this app. That was a bad example of autocomplete. Right. Maybe autocomplete isn't actually working yet properly. So, and then if I plot X, we have a simulation of the stock market. Okay, thank you very much. This is just a small example of the sorts of things you can do. You can also download stuff off the web run that. You can, as you can see, we have collaborative presence. You can see where people are. If someone else opened this, you'll see where they were. And you can also publish things, so you can make a read-only version that anyone can view. So I'm going to turn it over to questions now.